speaking on Newman's conjecture.
Hi everyone, thanks for coming to my talk. I'm Alan. I'm currently a senior at Princeton. I'll be starting at Chicago in the fall. I'm presenting on part of my summer research last summer as part of the small RU with Professor Miller. And it's on Newman's conjecture. So Newman's conjecture is a conjecture about the zeta function. And we'll give some background about it in this talk, and we'll see why it's considered an almost counter conjecture to the Riemann hypothesis.
Is this DJ Newman or a different Newman?
I'm not quite sure.
This is the advantage of the wind. So,
Okay. So this last summer, I was looking at what happens when we study Newman's conjecture in the function field setting, so I'll be presenting on that as well. So first, here's the Riemann zeta function. Because of this factorization to primes, that's why number theorists care about it so much. We want to know where the zeros are. So that's what the Riemann hypothesis hypothesizes. And people have been trying to prove this for a very long time. One way to make the Riemann hypothesis a little easier to phrase is to define these auxiliary functions this way. First, we use little c to complete the zeta function. And then big C will be the completed zeta function on the critical line. So when you do this, what happens is we get a function that maps reals to reals. And the Riemann hypothesis is equivalent to the statement that all the zeros of C of x are real. So we don't have to worry about things like trivial zeros. And using this function, Polya had an idea to try to prove the Riemann hypothesis. First, he took the Fourier transform of this function, and then he inserted a parameter e to the tu squared. And then he applied the Fourier inversion. So what this gives us is now a family of functions in x indexed by t. And when t equals 0, we get back our original function because of the Fourier inversion formula. And then De Bruijn and Newman show that there exists a constant lambda, which we'll call De Bruijn-Newman constant, which divides the real line in half as follows. So if t is greater than or equal to lambda, then this function will have only real zeros. And if t is less than lambda, then Ct has at least one non-real zero. So actually what Polya wanted to show was that for all t, this function had only real zeros. In other words, this whole thing would be blue, but turns out not to be true. But anyways, here's our picture. And Riemann hypothesis, if you remember, is equivalent to the statement that C0 has only real zeros. So this is the same thing as saying that 0 has a lie in this blue region over here. In other words, this is equivalent to the statement that lambda is less than or equal to 0. So we can phrase the Riemann hypothesis in terms of this constant lambda. And since Newman's conjecture is an almost counter conjecture to the Riemann hypothesis, it's probably not surprising to see that it's of the form lambda is greater than or equal to 0. And this is what Newman said himself. The new conjecture is a quantitative version of the dictum that the Riemann hypothesis, if true, is only barely so. So here's our family of functions again. If we view it as a function in x and t, we'll notice that it satisfies this partial differential equation. This is a lot like the heat equation, except there's a plus sign instead of a minus sign. So we'll call this the backwards heat equation. And to get an idea of how this helps us, we can look at something simpler that solves the backwards heat equation, namely this function here. So what we'll do is let's plot this function for free values of t and see how it changes. So let's start at t equals 0. Notice that it's a periodic function, so we plotted it for one period. And because of the cosine 2x, we expect there to be 4 zeros in this period. And we can see them very clearly over here. Now we're going to move time backwards and see what happens to this function. So let's move t down to the negatives. In that case, the function looks very similar, except the sharp peaks got a little smaller. And if we keep doing that, it keeps happening. And we can use the backwards heat equation to explain this. Because we're moving t backwards, it's as if we're solving the forwards heat equation. So if we think of this as temperature, then these really hot areas are getting a little cooler, these really cool areas are getting warmer. And when we look at the zeros, let's see how they move around when we change t. So here, these two zeros, x1 and x2, as we keep moving time back, they get closer and closer to each other. And eventually, they bump into each other at 0, at this very special time. And now, if we keep moving time farther back, we know that this thing is going to go down, so these two zeros have nowhere to go. So they end up becoming complex. So what has happened is, as we move time backwards, the zeros, they got closer and closer to each other, and then they popped off the real line. And so actually, at this particular time, t0, we have this property that this value satisfies the function, it divides the real line into these two halves, very much like the case with the Riemann zeta function. And so this kind of gives us a reason to understand why such a constant lambda would exist. So back to that constant lambda. So people have been able to compute lower bounds for lambda. So recall that a lower bound of 0 would prove the Newman's conjecture. A positive lower bound would disprove the Riemann hypothesis. So luckily all of these have been negative, and they've been getting closer and closer to 0. Notice that in 1994, the bound was significantly improved. This was due to a method of Sorda, Smith, and Varga. Their idea was to look for unusually close pairs of zeros on the critical line of the zeta function. Because if you think about our example, very close pairs of zeros, they might bump into each other and then pop off the real line. Last year, Stoffel showed that we can do the exact same setup, introducing the parameter of t and getting this constant lambda with these quadratic Dirichlet L functions. In that case, each L function, Ls chi d, gives us a de Bruijn-Newman constant lambda d. And we would like to conjecture that all of these are non-negative. But trying to show something like this is just as hard as showing the Newman conjecture for the zeta function. So what Stoffel looked at was the weaker conjecture that the supremum of these constants was non-negative. And this allowed him to look through lots of values of d at once. And in particular, he found that for this value of d, he got a pretty good bound on its constant. And his idea was to look not for unusually close pairs of zeros off the critical line, or no, far along the critical line, but to look very close to the central point. If you can find a very low-lying zero, then its reflection will also be there, and they'll be very close to each other. So that gives you a close pair. So this summer, I started off by thinking about what was it that lets you generalize the Newman conjecture setup with the parameter t and all that. And it turns out that what we need is for the L functions to satisfy what I'll call the nicest symmetry possible. In other words, this S goes into 1 minus S perfectly. So most L functions will satisfy some kind of symmetry involving S and 1 minus S, but it won't be as nice. For example, if the L function is not self-dual, or if the root number is not 1, then we can't really do this setup. And so we look for L functions with that kind of symmetry. And very quickly we can find automorphic L functions that satisfy that nicest symmetry. And then we can do the same setup, and we'll get a constant lambda for each automorphic L function, and then we get stuck again. So let's move on, and we go on to function field quadratic L functions. So first of all, they do satisfy that nice symmetry, and actually we can find a lot more interesting behavior here. So let's talk about function fields now. We'll let Fq be the finite field with Q elements. And we'll need to assume that Q is odd in this case. And Fqt will be the ring of polynomials in T. So the general idea is that Fqt in the function field setting behaves a lot like Z in the number field setting. In other words, we can do a lot of number theory on Fqt in the same way that we do it on Z. For example, in Fqt, there's the notion of prime, there's Fermat's little theorem, there's Euler's theorem, there's the prime number theorem, there's quadratic reciprocity, all that stuff. And in particular, there are quadratic Dirichlet L functions. In this case, when we complete the L function, we do see that it satisfies this really nice symmetry. So we can do the Newman conjecture setup. And as a bonus, we actually have the Riemann hypothesis for these L functions. This was proved by Weil in the 1950s. And this gives us an idea that, in general, in function fields, things are easier than in number fields. Not that this was a trivial proof or anything, but the fact that we can actually prove the Riemann hypothesis in the function field setting is a pretty good indication that function fields are easier. So we'll move on to define C of x as before. So it'll be the completed L function on the critical line. And it turns out that it has a very nice form in the function field setting. It's just this finite sum over cosines. And these phi zeros to phi g can be computed explicitly very easily. And then we can follow Pauli's setup again, where he took the Fourier transform and then had this parameter t, and then went back. In this case, we take the Fourier transform on the circle because we have periodic functions. So what ends up happening is all we end up doing is just putting an e to the t n squared factor here. So we still have functions that are very easy to work with, even after inserting this parameter t. If you recall our example from earlier, this was actually a ct of x for this particular value of d. And if you recall, we have this very specific time where it divides the real lines of these two halves. So this time is, in fact, the Newman constant for the L function associated to d. And what's important here is that we were actually able to calculate lambda d. So here, this is an approximation, but it's actually the log of an algebraic number of degree 4. So we know what it is exactly. So the fact is that we were able to calculate it, and imagine if we could calculate lambda for the Riemann zeta function. Then we would either prove or disprove Newman's conjecture, and more importantly, we would prove or disprove the Riemann hypothesis. But that seems a little hard, so let's go back to lambda d. One thing we do notice about lambda d is that we got a negative value. So if you recall what the Newman conjecture is for the Riemann zeta function, it was that this constant is always non-negative. But we got a negative value in this function field case. So we have to ask, is that expected? Or is there something weird going on here? And if we think about it a little bit in terms of closed pairs of zeros, we have reasons to believe that, well, it's not too much of a surprise that these lambdas are negative in the function field case. The reason is, in the number field case, as you go far along the critical strip, you will find, or the critical line, you'll find closer and closer pairs of zeros. Or you expect to find closer and closer pairs of zeros. This is related to Montgomery's pair correlation conjecture and all that. But in the function field case, because we have a periodic function, as we go along the critical line, we'll see the same thing over and over and over again. We're not going to find anything smaller or closer. And that translates to having a constant that's negative. So we don't want to make the conjecture that all of these lambdas are non-negative, because it's not true. So instead, this is when we can look at what Stoffel did, and recall that he considered an entire family, and he looked at their supremos, and then made the conjecture that those are non-negative. So in our case, we can do the same thing. In different kinds of families of L functions will give you different versions of Newman's conjecture in the function field setting. For example, you can fix Q, the size of the finite field, and let D vary over all FQT, and look at that supremum. Another example is to fix D, the degree of the polynomial, and now we can let Q vary, and then as we vary through all the polynomials there, we can make the conjecture that that supremum is non-negative. In general, we get the same principle that Stoffel had when he was looking at the number field case. In other words, you look at the small zeros, and that can give you information on lower bounds for the constant. In this case, if the first zero is unusually small, and the second zero is roughly where we expect it to be, then we do in fact get a lower bound on the constant. So low zeros give us good bounds on lambda d, just like in the number field case. And in general, because of connections of how the distributions of zeros seem to correlate with distributions of eigenvalues of random matrices, we expect a lot of low zeros to occur within any family. But none of that is actually known. So let's actually prove something here. So first, let's look at another version of the Newman's conjecture in function fields. In this case, we're fixing a polynomial with coefficients in z, and for each prime, we're reducing it mod p to get a polynomial in fpt. And so unlike the other cases where we have lots and lots of polynomials, here we only have one for each prime. But in any case, we can still ask whether the supremum of these constants is non-negative. And let's start with an easy case. Let's start with degree d being 3. In that case, we end up with this very simple form for our functions ct of x. This constant a, p of d is the trace of Frobenius of the elliptic curve y squared equals d. So we start to see things from number theory coming in. And from this expression here, it's not too hard to see that our constant lambda dp, remember this is the constant that separates when the function has only real zeros and when it doesn't. The constant is given by this. We just have to look at when this thing has real zeros or not. And this constant might look very familiar to many of you because in the 1930s, Haas showed that that ratio is strictly less than 1. And we want to ask what the supremum of all of these is. So we need to know not just this bound, but we need to know what the distribution is of that ratio. So what is the distribution? And this is what the Sato-Tate conjecture is about. So if you're not familiar with the Sato-Tate conjecture, let's pretend that we're not. And let's see what it is actually saying. The idea is if we start with any square-free d with coefficients in z, and we compute this ratio APD over 2 root p for all the primes, or for many primes, then let's look at how those values are distributed. We'll see that we get either one of these two following distributions. Either something like this, which goes from -1 to 1, and has a sharp peak at 0, or we get this nice semicircle, which goes also from -1 to 1. And it's not hard to show that if d has complex multiplication, we'll get this distribution on the left. But if d does not have complex multiplication, then it's harder to show that we get this thing. But this was proved recently in 2011. And so this is a special case of the Sato-Tate conjecture. And because of the Sato-Tate conjecture, we actually can prove that for this particular family, where we fix the polynomial d with degree 3, we do get that the supremum is non-negative, or actually just 0. And the proof goes like this. We know how the primes, or how this ratio is distributed. It's either this one or this one. And in either case, we can find the sequence of primes such that this ratio tends to 1. And therefore, the log of that ratio will end up tending to 0. And so the supremum here will be 0. And so that's pretty exciting that we can actually prove Newman's conjecture for some particular family. And that's about it. So if you're interested, here is the paper that we wrote up after the program ended. It says submit it. I just learned 10 minutes ago that it's been accepted today. So, okay.